As a study guide for exam number 2, let's try to solve a set of old exam problems. Number 1, find the absolute maximum and minimum values of f over d. D is the unit disk of radius 1, and f is given in this way. To find the absolute maximum and minimum values, we have to find local extrema inside and on the boundary as well. Here, first, try to find inside. Okay, in order to do that, we start with gradient of f. Now, in x directional derivative is 2x minus 4. And y directional derivative is 2y. We set it 0, then we can get x is 2 and y is 0. Okay, this point is out of the domain, so there is no inside local extrema. Okay, let's move on. Boundary. Okay, there is boundary. Okay, that is x squared plus y squared equal 1. So along with that, f becomes, now that is 1, so that's 1 minus 4x. Now x is moving from minus 1 to 1, so that when x is 1, the value is minus 3, and when x is 1, okay, minus 1, then f must be 5. So minus 3 will be minimum, and 5 will be maximum. That's the final answer. Or you can solve this problem by using Lagrange multipliers. Okay, that is a function f, and that is the constraint. So that here, if you are trying to use Lagrange multiplier technique, then gradient of f must be lambda gradient of g. Right? So already we know gradient of f, which is 2x minus 4 and 2i, and lambda and gradient of g is 2x and 2i. Okay, there is first equation, second equation, and the constraint must be third equation. Now, from equation 2, okay, there's 2i equal lambda 2i. If we move this one to the other side, then 2i 1 minus lambda equals 0, which means that y equals 0 or lambda equal 1. Now, lambda is 1, okay, y equals 0. Then from equation 3, x must be plus minus 1. From this one, y is 0, so x squared is 1. So, and then 1. How about lambda is 1? Then, okay, in this equation, that is now lambda is 1. Then equation 1 is saying that is 2x minus 4 equal 2x. Okay, this is impossible. So we have only the choice y equals 0, x is plus minus 1. So if you use this value, y equals 0, x is 1, then the value is minus 3. X is minus 1, then the value is 5. That is exactly the same as this minimum and maximum, right? You can get the same solution. Now, second problem is asking you to use the method of Lagrange multipliers to find the maximum and minimum values of f subject to that one. Okay, let's try to solve it. We start with gradient of f equals lambda gradient of g. Okay, that is x derivative is 2x, y derivative is minus 2y. Okay, equals lambda times this one, there's 2x, and now it's 2y. So we have 3 equations. Okay, let's try to write down 3 equations. That is 2x equal lambda 2x, and second one is minus 2y equal lambda 2y, and third one must be the constraint. So that is x squared plus y squared equal 4. Number 1, number 2, number 3. Now if you focus on number 1 and number 2, then okay, lambda, for this one, lambda must be 1 or minus 1, right? So the lambda must be plus minus 1. Okay, we reached that one. When lambda is 1, okay, from here, okay, lambda is 1, then lambda is 1, then y must be 0. That's from the second equation. Lambda is 1, then y must be 0. Y 0 means that from equation 3, y is 0, then x is plus minus 2. Once lambda is minus 1, then now from equation 1, x must be 0. That means from equation 3, y must be plus minus 2, right? From here, x is 0, then y must be plus minus 2. So we have 4 points. That is, now it's circle of radius 1, radius 2, that is the constraint. That's 2. Y equals 0 and plus minus 2, this point, that point. Now x is 0, then plus minus 2. At these 4 points, you have to get the values. Okay, let's try to get the values of f. Here, that is x is 0, y is 2, then from this one, and f value must be minus 4. Again, here the same, f must be minus 4. Over there, y equals 0, x is 2 or minus 2, and f will be 4. Here again, f will be 4. These are extreme values, so that minimum is minus 4, maximum is 4. Quite simple, right? Number 3, in evaluating a double integral over a region D, the sum of iterated integrals was obtained as follows. Okay, we have 2 portions. Sketch the region D and express the double integral as a single iterated integral with reversed order of integration. Okay, let's try to solve the problem. Okay, now that is this is part 1. Now that is part 2. Let's say. Now for part 1, we are solving A. Okay, that is x direction. This is y direction. Okay. Now x is moving from 0 to 1. That is dx, and 0 to 1. So x is moving from 0 to 1. Now for each x, y is moving from 0 to x. Okay, bottom y is 0, top y is x. So the y equal x is this one. So the bottom y is 0, top y is x. That is y equal x. So we have this region from part 1, right? Okay, now how about part 2? Now x is moving from 1 to 2, so from 1 to 2 here, and this region, and y is, now bottom is 0, bottom y, and top y is 2 minus x. Okay, 2 minus x is this one. That is y equal to minus x. So that region, this is from part 2. Okay, we visualized and sketched the domain there. Now, let's try to express the double integral as a single iterative integral. In order to do that, you have to now get the iterative integral and y direction integral and out integral. It must be out integral. So the given integral must be, now that is height is 1, in y direction is moving from 0 to 1, so that will be dy y direction. Now in x direction, for each y is moving from 0 to 1, for each y, that is bottom y, this is top y, from here to, in fact, bottom x, top x, right? Bottom x is y, x is y, top x is 2 minus y, right? For each y moving from 0 to 1, for each y, now this region can be covered along with this one. This is a bottom x, top x. Bottom x is y, top x is, from here, x is 2 minus y, right? Okay, so now f is given and dx. That's the answer for part B. Okay, now number 4, evaluate the iterated integral by converting to polar coordinates. First, you have to recognize the domain. Now in x direction is moving minus 2 to 2. So let's see what it is. Okay, yeah, this is y-axis, and x is moving from minus 2 to 2. For each x, now y is from this one to 0. Okay, so it's a bottom portion. So that means, okay, this means, in fact, y is moving minus square root of 4 minus x squared to 0. This portion is the same as, now squaring, we have x squared plus y squared equal 4. Of course, here y must be non-positive. Okay, so that is the region must be this one. Here, the circle of radius 2 and only lower part. That's region D. Okay. Now, this is polar coordinates, so the given integral must be same as. Now, theta, okay, that is pi to 2 pi. This is pi, and that is 2 pi. And then r is from 0 to 2. And cosine, that is cosine x squared plus y squared is r squared. And this is dA, dy dx is dA. That must be changed to be r dr d theta. Now, that is a theta independent. So the out integral has 2 pi minus pi immediately, so which is pi. And we try to get now integral for that one. Okay, so here antiderivative, the major part must be sine r squared, right? And if you try to make a derivative, then that will be cosine r squared and then 2r will come out. So this is extra, so you put here half. Then this whole thing will be an antiderivative of that integrand. Now we are evaluating from 0 to 2. So we have, this is pi, and we have what, half, and then now sine, okay, sine 4 minus sine 0, that will be 0. So that this is the final answer. It's not so much complicated, right? Okay. Now we'll go number 5. Suppose x and y are random variables with a joint density function. F of xy is given in this way. So it is non-zero only in unit square. Now otherwise it's 0. First we have to find the constant k. For the function f to be a joint density function, the integration must be 1, right? And clearly the values are non-negative and integration must be 1. So integral of f over R2, that must be 1. Now, because outside is 0, we can get the integral only integrating over this region. So the x is moving from 0 to 1, and y is moving over in 0 to 1, and now the integrand is k x squared y and dx dy. Right? It is separable, and k is constant, and x direction from 0 to 1, now x squared dx. Now y direction again 0 to 1, y dy. Now from here, k times, that is 1/3, and that is half, so that now that must be 1. Anyway, that's k over 6, which implies that k must be 6. So that's the answer for part A. And how about part B? We decided already k value, and we try to get x mean and y mean. Okay, what is x mean? Mu1 is defined to be like the integral. Now let's say there's a d, integral over d, and x times f, right? And dA, that is definition of x mean. For this one, now integral over d, and already we know it's k is 6 and x is multiplied, so k, now x cubed and y and dA. Okay, k is 6, so we have a 6, and now it is again separable. So we can write this one from 0 to 1, x cubed dx times, and integral from 0 to 1, and now y dy. From here, 6 times 1/4 times 1/2. Yeah. So we have here, you can get it, right? And that is now 3/4, right? Okay. How about mu2? It's defined to be here, integral over the y times f dA, which is same as integral, double integral over d, and k is 6, and x squared, y squared, and y is multiplied, and now dA. So it is 6, and okay, again separable. From x squared integration, we have 1/3, And from y squared, again, we have 1/3. So that is 2 over 30, right? No. Okay, yeah, 2 over 3. Okay, so mu2 is 2 over 3, and mu1 is 3 over 4. That's the answer. Okay. Let's go to the final problem. Find the surface area of the part of a plane. Okay, that the problem is made in 2022. So we have here a big number that lies inside the cylinder. Y squared plus z squared is 1. We have a warning. The cylinder is not vertical, but rotate to the direction of the x-axis. Okay, yeah, let's try to visualize the surface. Okay, there's x direction, there's y direction, there's z direction, and we have right now a cylinder in x direction like that. So we have such a cylinder, and then it is cut by, in fact, the plane is now, somewhere it is made, and then it cut here, the plane will cut the cylinder, and somewhere it will be cut in this way. So for this surface, we have to get the surface area after cutting this cylinder. Now, for this problem, we may consider the domain as that area, so that this is a domain in y-z plane, and it's a polar region. And then, so that height must be a function of x. So we may write down here x equal, now from this one, 2022 minus 3y minus 15z. Of course, that is f of here yz. And domain is along with yz, and we have f of z. And we make such a surface right now, and defined over this domain, of course, inside everything. Okay, so the formula for surface area is given in this way. The surface area is integral over the square root of, when we consider the function z is f of xy, that's f sub x squared plus f sub y squared plus 1, right? Now, the function is function of y and z, so that f sub y squared plus f sub z squared plus 1 and dA. That's the formula of surface area. So it's a simple integral over d, and y derivative is minus 3, so that is 9, and this is 15, z derivative is minus 15, so that 15 squared is 225, right? Okay, now plus 1, right? Okay, dA. This one is square root of 235, and constant, it can go out, and integral over d and dA. Now, this is region, the circle of radius 1, so we know that the area, this is area of the region D, and it must be pi, because it's a disk of radius 1. So square root of 235 and pi, right? So that's the final answer. Okay? Okay, that's the end of the study guide. Thank you.